Still working. Okay, so hi everyone, my name is Naama, and I'm going to talk about low complexity cryptographic hash function. And this is a joint work with Benny Applebaum, Yuval Ishai, Eyal Kushilevitz, and Vinod Vaikuntanata. Okay, sorry about that. Okay, so cryptography is basically the science of useful hardness, right? So, and its hardness comes from unsuccessful attempt to find efficient algorithm to important problems as factorization, discrete log, and lattice problems. And we want crypto to be as simple as possible, right? In NC0 class, or even can be calculated by Homer. And we concentrate in a hash function. And the main goal of this function is to shrink the input while still preserving important properties of a random function. Okay, and the goal of this function is to make cryptography much more efficient. So we want to be able to calculate this function efficiently. And we say that a function is collision resistant if the probability an evil adversary, think about it as a probabilistic polynomial time algorithm, can find a collision is negligible. Which basically says that we don't want him to be able to find two different messages that have the same output, except negligible probability. Okay? And against non-uniform adversary, we allow this function to be picked at random, right? Because otherwise, a non-uniform adversary could just output a fixed collision. And we're also going to talk about universal one-way hash function, which one of the input it be picked at random. Okay, but in this talk, when I say hash function, I refer to collision resistant by default. Okay, so this function have many applications in cryptography. For example, in signature. Instead of signing a long message, we can hash it first and then sign on the short output. Instead of proving a long NP statement, we can prove a short NP statement by implying collision resistant on the statement before. So we want to study computational simple hash function, and we consider several measures of simplicity. So one is the degree, where each output bit is a degree D binary function of the input bits. Okay? Output locality, where each output bit depends on at most the input bits. Similarly, input locality and circuit size. Now notice that the output locality gives us a bound on both the degree and the circuit size. In particular, when the output locality is constant, we get constant degree and linear circuit size. Okay? And Applebaum et al. Showed that under standard cryptography assumption, there are collision-resistant hash functions with constant output locality as small as 4 and constant degree as small as 3. Okay, but the problem is that the shrinkage is sublinear. Think about it as a function from n to n minus little o n bits. Okay, so it cannot be used in application as signature and zero knowledge. Okay. Applebaum and Moses show a degree 2 construction of universal one-way hash function with linear shrinkage and constant locality. Okay. So in our work, we want to understand what we can and can't do with low complexity when the shrinkage is at least linear. For example, from n bits to half an n bits. Okay, so first let me go over the result under plausible assumptions, and then I will discuss the assumptions. Okay, so it's easy to show that nothing can be done for degree 1. It's just like solving a linear equation. Okay? We show a degree 3 construction and a constant locality construction. So let me remind you that constant locality implies linear circuit. So by applying hash tree on this circuit, we can even get arbitrary small shrinkage, for example, from n to square root n bits, okay? And still maintain the linear circuit complexity. We also show a degree 2 universal one-way hash function construction. But like Alessandro said before, the question on the existence of degree 2 collision-resistant hash function remains open. And we leave this question open even with 1-bit shrinkage. Okay? And we show a partial negative evidence by showing that a random degree 2 mapping is not collision-resistant. Okay, now let me go over the assumption. So in degree 3, we assume the hardness of syndrome decoding over random linear codes. By using a strong variation of this assumption, we can also get the constant locality. Okay? For degree 2, we assume the hardness of the MQ problem, which roughly say that a random degree 2 mapping is not invertible. So from now on until the end of the talk, I'm going to discuss about the degree 3 construction. So let me introduce you the new assumption we use, the binary shortest vector problem. And in the assumption, so we assume that given alpha n by n random matrix, finding a vector with relative Hamming weight delta in A's kernel is hard. And we can think of this problem as analog to Ajay shortest integer solution problem, but over the binary field. Okay, so how can we assume this problem is hard? We already showed that in the worst case, it's NP hard. And we know that when A is random, from Gilbert-Vershamov bound, when delta is smaller than the inverse entropy function, there is no solution. On the other hand, when delta is larger than half n alpha, we can find solution efficiently. Okay? So we want to use the hardness of this gap. Okay? And as far as we know, all known algorithms run in exponential time. Okay? It's also not hard to show in cryptographic view that the hardness of this problem implies the existence of one-wave function. Okay? And by reducing the gap to twice the inverse entropy function, we show the degree 3 construction. And we do it in 2 steps. The first, we show a constant degree construction, and then by applying perfect randomized encoding on that construction, we lower the degree to 3, but we still maintain the linear shrinkage. Okay, but I'm not going to specify about this step in this talk. Okay, so let's start with a short warm-up, something that doesn't work. So we know that the range are alpha n vectors, but the question is, what is the domain? Okay. So if we just take n-length vector and multiply it by the matrix, this function is not collision resistant, right? If we shrink it to low-weight vectors and then apply the matrix, so we do get collision resistant, we get the compression, but this mapping have high degree. Okay, so it's the short blanket problem all over again. What we're going to choose, our upper body or lower body, right? So luckily, we can expand blankets, but we can expand vectors. And we expand it in a way that guarantees that the expand vector have relative Hamming weight half a delta. Okay, so we want the expand to have, obviously, right, small degree. We want it to be injective and economical because we need to shrink it after. Okay? We also want this expand to be in NC0, but this is for the next step that I'm not going to discuss. Okay, now notice that finding a collision on this function, it means finding z vectors that have the same output on A. But since this function is injective, those vectors are different, right? And since we bound the weight of each vector to half a delta, we can bound the difference weight to delta. And from linearity, obviously the difference in A kernel. Okay, so notice that finding a collision implies finding a vector with relative Hamming weight at most delta in A kernel, which we assume is hard. Okay, and on this, like I said before, the next step is applying on this construction perfect randomized encoding, but I'm not going to discuss this here. Okay, so let's just summarize and talk about open problems. Okay, so like I said, under different flavors of the binary SVP assumption, we were able to show a low complexity collision resistant hash function with at least linear shrinkage. And we also show in the paper win-win result by showing that breaking our construction will have useful consequences in learning algorithm and data structures. Okay. And the main open question is, does there exist degree 2 collision-resistant hash function? And we also relate this question to the question of the existence of degree 2 randomized encoding and degree 2 statistically hiding commitment. Okay. Thank you.
Any questions while? Yep.
So is this binary key the same as learning all the attribute-efficient learning of parities, that you basically need to find a short parity consistent?
Yeah.
So it's the same problem?
Yeah,
okay.
exactly.
It's known to be, kind of assumed to be hard in learning theory too. So.
Yeah, it was surprising that this problem seems so natural, but it wasn't like a standard cryptography assumption, as far as we know.
What's your belief? Like should there be?
I believe no.
Okay, so I think that the random degree 2 negative result is.
I think so, but I change it a lot.